In class today, you were introduced to the idea of logistic curves. And logistic curves come from the differential equation in this form. dy dt equals ky parentheses p minus y. And you were given the initial conditions of one person knew the rumor at times equals 0, and after 1 day, 100 people knew the rumor, and there were 1,300 people in the school. And after you used your separation integration techniques and your partial fraction knowledge, you came up with this equation right here, y equals 1,300 over 1 plus 1,299 e to the negative 4.684 t. And the purpose of this video is to really take a look at logistic curves and figure out why they behave the way they behave. So the first thing we're going to do is we are going to use our graphing calculator to graph the curve. So I typed it in, and when I hit graph, I only got a small little piece of the curve. I don't have a really good idea of what this curve looks like. So I'm going to change my viewing window to 0 my x min, 6 is going to be my x max, and I'm going to go zoom fit, so zoom 0. And what that does is it fits my viewing window to fit the whole curve between x values of 0 and 6. So here we have the logistic curve, and I'm just going to copy what this graph looks like. And if I check my table, I realize that it tops out at about 1,300. So explain the logistic graph and examine the logistic graph and consider why it behaves as it does. Specifically, use your logistic equation to find the y-intercept and the limit as x goes to infinity of the function y of x. So to find the y-intercept, you plug in 0 for t, and our y-intercept ends up being 1. Our y-intercept represents how many people knew the rumor when it started. So this is right here at 1. And then we're going to take the look at the limit as x approaches infinity. Or sorry, this should be t. As time is going to infinity. What is our curve doing? And what's happening here? 1 plus 1299 e to the negative infinity. E to the negative infinity is the limit is equal to 0. So what we end up with is 1,300 over 1. And what this limit represents is the maximum population. There are only 1,300 students in the school, so only 1,300 can learn about the rumor. So it's going to top out at our maximum population, which is 1,300. Use your calculator to sketch the graph of the derivative of the logistic function. So we're going to go back to y equals, and I'm going to use the n-deriv function in my calculator. So if you go to math 8, we're going to get this derivative function in here. And to plug it in, we want d dx of this function here. So instead of plugging it all in again, you can use the vars button. So vars, go over, hit function y1, and we want that with respect to x. So that's how you do it in the TI-84. If you have the older version of the calculator, then what you do is you hit math 8, and it pops up a little bit differently. Vars y1, and then with respect to x, starting at x. So this will get you the same result as this does. As we hit, I'm just going to hit zoom fit again, just in case my derivative doesn't fit in the window. There's the logistic curve. And here's the derivative. And here we have our derivative. And the question is, explain why the general shape of the derivative graph is reasonable. And the reason why it would come up, so it's increasing up until about halfway. And once the population of the people who know the rumor reaches about halfway of the max capacity, the slope becomes negative. And the reason why is because there's less of the population that doesn't know the rumor already, so there's less people to share it to, so it's going to start coming down. So again, it should peak at the same time that half the population has heard the rumor. Next problem, what are the coordinates of the maximum of the derivative? So I'm just going to use my calculator to find the maximum of the curve. And the maximum occurs at 1.531, comma 1522.297. So I'm going to sketch this curve onto my graph. And what are the units? So this unit represents the time, and this is a rate. So this is how many people per day are hearing the rumor. So this is people per day. So at 1.531 days, we're maxing out the derivative, and the derivative represents the number of people per day who are hearing the rumor. So then use the x-coordinate found in part C to find the corresponding y value in the logistic curve. So I can go back to my calculator, and I know that the answer is stored in my x value of my calculator. So what I can do to find the value of the function is I can go to the function y1 and then do parentheses x. So what your calculator is doing, it's plugging in 1.530, all of this into our first function, and we're ending up with the rumor spreading the fastest. At 1.531 days and 650 people have heard the rumor. And it does logically it makes sense that the halfway point, when half of the people have heard it, it's spreading the fastest, because at that moment, a considerable amount of people have heard the rumor, but the second half of the population hasn't. So there's a lot of people telling the rumor, and there's a lot of people who haven't heard it yet. So this is when it's moving the fastest. So what's the difference between exponential growth and logistic growth? The bacteria question was an exponential growth, and the rumor question was logistic. Explain the difference between logistic and exponential growth, and that has to do with carrying capacity. And what the carrying capacity is, it's like a maximum population. The exponential growth happens when there is no limiting factor, where it can just keep on increasing without limitation. But the logistical growth has a carrying capacity. There were only a limited number of students who could know the rumor. So then we end up with this shape of a curve. The limit as exponential growth goes to infinity is infinity, but the limit of logistic growth is this max population. In what context would we ever have this? So it all has to do with whether or not you're limited by any factors. This one is unlimited growth. And then this one has a limited capacity.